You know, when you really try to describe the world around us, it feels like we're missing a piece of the puzzle, right? Well, today, we are finding that missing piece. We're going to go way beyond just simple numbers to really get a grip on motion in all its real-world, multi-dimensional glory. Okay, let's dive right in.
So, let's kick things off with a simple scenario. Imagine the weather report says the wind is blowing at 15 miles per hour. That sounds pretty straightforward, doesn't it? But does that one little number really tell you everything you need to know?
Well, if you're a pilot, the answer is a big, fat no. See, 15 miles per hour is just its speed. Is it a headwind that's slowing you down, a tailwind speeding you up, or maybe a crosswind pushing you totally off course? That direction is every bit as important as the number, and that's the exact problem we're going to solve today.
And that right there brings us to our first really big idea. Some things in physics need more, a lot more, than just a number to be fully described.
And this slide, well, it lays it out perfectly. On the left, we've got scalars. These are the simple values we use all the time, like speed or temperature. But on the right, we have vectors, and they add that one crucial piece of information, direction. So it's not just 60 miles per hour, it's 60 miles per hour north. It's not just a 10 Newton force, which is just a fancy way to say a push or a pull, it's 10 newtons down. You see? That direction changes everything. So to get just a little technical for a second, a scalar quantity is just that, a single value with a unit. Mass, speed, time, they're all scalars. They're simple, they're straightforward, no fuss. And here is the star of our show, the vector. It's got a number and a unit, we call that the magnitude, but it also has that all-important direction. Velocity, acceleration, force, these are the powerful tools that let us describe the world as it really is. All right, so we know what vectors are. Awesome. But how do we actually, use them? Let's open up the toolkit and see how we can work with these new concepts. The secret, you'll be happy to hear, is surprisingly simple. We can take any vector, no matter what kind of weird angle it's pointing at, and break it down into two super easy to manage pieces. How much of it is going left and right, in the x direction, and how much is going up and down, in the y direction. We call these its components.
Now, to keep track of these directions, we use these special little labels called unit vectors. This I hat guy points in the x direction, and j hat points in the y direction. They're called unit vectors because they have a length of exactly 1, so they don't change the size of our numbers at all, they just give them a direction. Really, just think of them as signposts for the horizontal and vertical parts of our vector.
And this is the beautiful parts. This whole component idea makes adding vectors incredibly easy. I mean it. You don't need any complicated geometry. You just add the x parts together, and then, completely separately, you add the y parts together. That's it. It's that straightforward. Okay, check this out. Let's make this real. We've got vector A and vector B. To get our new vector, r, we just look at the x components. 2 plus 2 equals 4. Easy. Then we look at the y components. 2 plus a negative 4 gives us negative 2. So our brand new vector is just 4i minus 2j. See? Simple as that. So, we have our toolkit. We know how to use it. Now let's put it to work and start describing how things actually move around in 2 dimensions. This is where it gets fun. First up, we've got displacement. Now, this is a vector that points from where something started to where it ended. And notice, it doesn't care about the long, wiggly path it might have taken to get there. Nope, it's just the most direct, straight line change in position. And here's the crucial link. If you take that displacement vector and you divide it by how much time it took, well, you get the average velocity. So, because displacement is a vector, velocity has to be 1 too. And its direction? It's the exact same as the displacement. Okay, but we're not done. Let's take it one step further. Acceleration is the change in the velocity vector over time. And this is where things get really, really interesting. Because see, a vector can change in more than one way. This right here is a huge takeaway. Seriously. We usually think of acceleration as just speeding up or slowing down, right? But you are also accelerating anytime you change direction, even if your speed stays perfectly constant. That's right, every single time you turn a corner in your car, you are accelerating.
So, with that in mind, let's put our vector toolkit to the ultimate test, describing motion in a circle.
See, on the left, you've got this abstract physics diagram. It looks complicated, but on the right, that's just a car in a roundabout, something we've all seen before. And guess what? The physics is exactly the same. It's a perfect, real-world example of 2D motion. And this brings us back to that kind of mind-bending idea we just talked about.
Even if that car's speedometer is totally locked in at a constant speed, the car is constantly, always accelerating. Why? Come on, you know this. It's because its direction is always changing, which means its velocity vector is always changing. And our vector toolkit can handle this no problem. The total acceleration of anything moving on a curve can be broken down into two components. There's a tangential part, which takes care of any change in speed, and a radial part, which is what's responsible for the change in direction. That radial part is always pointing toward the center of the curve.
And boom, here's a perfect example of all of this coming together in action. A car is speeding up as it goes over a hill. It has tangential acceleration pointing forward because its speed is increasing, and it has radial acceleration pointing downward toward the center of the hill's curve because its direction is changing. The total acceleration is just the sum of these two vector components. See, it all comes together. So think about it. We started with a simple question about which way the wind was blowing, and we ended up with this powerful toolkit for describing even complex curved motion. We've basically unlocked the physics of a two-dimensional world. But the real world, it isn't flat, is it? So what's next? Oh yeah, you guessed it. We're going 3D.